All right, so where we left off last time, we're going to start talking about how we find the actual limit. So this first theorem here is where I want to start. If the limit of a function, notice this is a function, and the function matches my sequence, so a function that matches my sequence, that's what this says right here, then all I've got to do to take the limit of my sequence is to take the limit of my function. So if my function goes to L, then my sequence is also going to go to L. I will write this as limit as n goes to infinity of a sub n equals L. Problems? Oh, it crashed, didn't it? Anything?
Yeah, it shows that.
Okay, and so this? Okay. All right. So the difference here is between what I was doing before, where I was graphing just the points, and now I'm looking at the actual curve that connects all of the points. So you've talked about this. You talked about this kind of thing in Calculus 1. Now I'm talking about this kind of thing. So do you notice what the difference is? The difference between this statement over here and this statement over here is that this is a continuous function f, which means it's a curve that does something. And I'm asking what happens as x goes to infinity of that curve. And this is a sequence, so it's just the dots. Okay? And so what I'm claiming is if you've got a function that matches the dots, then if you already know how to find the limit of that function, then you know how to find the limit of the sequence. It's what I said before, where if I had the limit as n goes to infinity of 1 over n, that's going to be the same thing as the limit as x goes to infinity of 1 over x. And while it looks like all I did was change the variable, remember that what's implied here is that it's only defined at 1, 2, 3, 4, 5, and so on, while this is defined at all real numbers. Okay? But they're still equal, and that's still 0. How many of you took calculus in high school? Okay, a couple of you. Now, I know I don't teach this, but because my wife is a high school calculus teacher, I've learned some new tricks that I didn't know before. Okay? One of them, I think, is helpful in this context, and I'm going to give it to you. I didn't originally plan to put in the notes, so you might want to turn to the back page between this page and this page. And I want you to write down this. So if you had a high school teacher who was, current and cool and going to all the latest trainings, they might have heard of Bobo Button HDC. It's one of these weird mnemonics that helps you remember something. In particular, it helps you remember what happens at infinity when you take the limit. Okay? Bobo Button HDC. I talked to my wife's high school calculus class. They all know exactly what this means, and they use it regularly. They're ready for their AP calculus test coming up in a month. Okay? Say it with me. Bobo Button HDC. Okay, what is Bobo? Bigger on bottom. And I'll tell you what this means in a second. Okay? Is 0. Well, I should say that's 0. Maybe you can remember that. It's not Z, but bigger on bottom is 0. Now, what do I mean by that? Think of it this way. If I had, I went too far. N squared over n cubed. Or if I had 3n cubed plus 4n squared over n to the 6th minus 1. I'm looking at rational functions In this case now, depending on n, I'm looking at the degree on top and bottom. Okay, so what's the degree of the top and the bottom? Okay, the degree up here is 2, and the degree down here is 3. Where is it bigger? Bigger on bottom. What about this one? What's the degree on top? It's the biggest one you see. It's the leading term. And on bottom? Okay, bigger on bottom. What does that go to at infinity? 0. Bobo. Bigger on bottom, 0. Okay? Button. What do you think that stands for? Bigger on top. Top. I think she says not exists, or maybe no. All right. Bigger on top? No. The limit does not exist. Okay? Meaning that if I had n cubed over n squared, or if I had 4n squared minus 3n, I keep writing x, n cubed divided by n plus 2. Both of those, if you look at the degree, which is the highest number, bigger on top, right? What's the degree on bottom? 1, it's understood. So, the limit does not exist. No. Bigger on top? No. Bigger on bottom? Bobo? 0. Bigger on top? Button? No. HDC. Exponents? Yeah, I forgot to for a second. Are the same. Divide coefficients. Right? EATSDC. All right, so if I had maybe 3n cubed over 2n cubed plus 1. I'll throw a plus 1 in there so you don't just cancel the n cubes. What does that go to? As n gets large, that gets closer and closer to 3 halves. The reason is because for large n, the top behaves just like 3n cubed. And the bottom, when you get really big n, that plus 1 does nothing. And when I say big n, I'm talking 10 to the 400th power. Okay? Really big numbers, a 1 makes no difference. Okay? So when they're really big, this is essentially 3n cubed over 2n cubed. The n cubes cancel, you get 3 halves. Okay? But do you see how that's each DC? Exponent on top, exponents on bottom. Exponents are the same, so you divide the coefficient, it goes to 3 half. Okay? Now, by the way, this also works for slight modifications of rational functions. Like if I had, let's say I had 3n cubed plus 2n squared minus 1 divided by the square root of 2n to the 6th minus 7n cubed. And I say, what does that do as n goes to infinity? Okay, well, Bobo Button HDC. So let's check the highest degree term on top and the highest degree term on bottom. What's the dominating term? What's the thing that's getting biggest, fastest? On top, it's this term right here, right? And what's the exponent? What's the biggest term on bottom? It's this 2n to the 6th, right? But it's the square root of it. So this down here behaves like the square root of 2n to the 6th.
So we can find out which one is getting smaller faster?
All I want you to check is the exponent. And I'm throwing the added wrinkle in there, you checking the exponent when you got a radical underneath there. Here's the point. If you look at just this term, and it's the square root of that, what's the degree of that term? What's the actual exponent? Well, it's 3 because the square root of n to the 6th is n to the 3rd. Do you see that? So if it's under a radical, divide that highest power, or that highest exponent, by 2. If it was under a cube root, you divide by 3. But you just get what the highest degree term on top and bottom looks like. Now apply Bobo Button HDC. Is it 0, is it non-exist, or is it the same? It's the same. So what does it go to? 3 over the square root of 2, or 3 root 2 over 2. Yeah.
The other terms do not matter.
For large n, they aren't significant. So it's what happens at infinity that you really care about. So that's why we only consider the highest degree. Only consider the highest degree or exponent, if you need to remember that. All right. So that'll come in helpful anytime you have to take limits at infinity, and we'll see that multiple times throughout this class. All right. You got all that? Can I go on to the notes now? We good? All right. Now, all right, just remember, our previous theorem said that if you had a function that matched it, then the limit of your sequence matches the limit of your function. My claim here is that the converse is not true. Just because a sequence converges doesn't mean its matching function converges. And the reason is I can do something like this. Let's say I've got a sequence, which is the points, that does this. That looks like it's converging to what? 0. Now, does that imply that every function that passes through these points converges to 0? Could you draw a function that passes through these points that doesn't go to 0? I mean, in your mind, you're picturing this function right here, aren't you? But if you're as creative as I was as a kid, connect the dots were too limiting for you. Why did you have to draw straight lines between the dots? Right? Why couldn't you do something like, oh, I don't know, this. Notice how, if I did that correctly, that function is passing through every single one of those points, right? Is that function converging to 0? Obviously not. Okay? So, just because you match the points doesn't mean your function converges. But if your function converges, then that means the points on your curve have to converge. See how it's different based on which way you state it? Here's another example. Remember, this one was 0, 0, 0. Remember that this as a curve is some kind of sine wave. In fact, it just goes through like this. Okay? Does not converge, and this does converge. So the point again is just because the function goes to 0, that it forces the sequence to, but just because the sequence goes to 0 doesn't mean the function has to. All of the same rules that we had for limits at infinity for functions apply to sequences. The limit of a sum is the sum of the limits. So like 1 over n plus 3n squared over 2n cubed plus 1. Just as an example on that first one. I won't do one for all of these, but the idea is there. by the way, do you notice I keep writing the limits two different ways? There's two notations that I use here. You don't have to write this down unless you need a reminder here. But there's two ways I write the limit of a sequence. I'll either write limit as n goes to infinity of something equals 0, or I'll write 1 over n goes to 0 as n goes to infinity. Those two things that I've written right there are exactly the same thing. It's just me, two different ways of writing the same thing. What generally happens, I'll be honest with you, is I start writing the sequence itself before I remember to write limit. So if I'm thinking ahead and I remember to write limit, I write it, but if I write 1 over n first, I usually don't have enough space in front of it to write limit, so I resort to this second form. But I want you to notice that I'm switching back and forth between notation. What's the limit as n goes to infinity of this sequence that I had on the other page? You've got two different sequences added together, right? And so it's going to be the first one, which goes to 0, plus the second one, which goes to Bobo Button HDC. Which one is it? Is it Bobo? Is it Button? Or HDC? It's Bobo, which means bigger on bottom, 0. You like Bobo? It's an easy thing to remember once you it sticks. It just makes life a little bit easier on those problems. I mean, the way that we used to, I think the way that I taught it, I'm wasting time. I keep wasting time. But the way that I taught it, you may recognize this, 3n squared over 2n cubed plus 1, is that you find the highest degree term in the whole thing and divide through by it. So multiply this by 1 over n cubed, and this over 1 over n cubed, and you get 3 over n on top divided by 2 plus 1 over n cubed, when you just multiply this n. And the n cubed came from the biggest thing in the whole fraction. Did y'all do it this way? Doesn't look familiar at all? All right, well, that goes to 0 over 2 plus 0, which is 0 over 2, which is 0. That's another way. Some teachers will just have you identify which are the biggest things on top and bottom, right? So this and this, okay? So this approaches 3n squared over 2n cubed, and then you reduce that, you get 3 halves times 1 over n, which goes to 0. I like Bobo Button. I'm just showing you some of the alternatives. It's a new one to try, is this Bobo Button. But the point I'm making here is that if you've got the sum of two sequences, you can just add up their limits. If you had subtracted them, you can just subtract their limits. If you have a constant times them, like this 3 halves, by the way, you can just pull the constant outside. So limit of a constant times a sequence is the constant times the limit. Limit of a constant is a constant, right? Like this 0 up here. If it stays 0 the whole time, then the limit is obviously 0. Limit of a product is the product of limits. Remember, we like limits for this reason over and above derivatives, right? Because derivatives have nasty product rules and quotient rules, but limits are nice. If you have the limit of a product, you can just take the product of the limits separately. If you have limit of a quotient, you can take them separately as long as the bottom doesn't go to 0. And if you have limit of a power, you can also take limit of the inside, then raised to the power. By the way, this means this also works for square roots. Right, so a limit outside of a square root can be moved inside of a square root. As a matter of fact, I'm going to jump down here. 7 says no matter what function that you have, if it's continuous, you can move the limit inside. So this could mean things like if you have the limit as n goes to infinity of sine of 1 over n. Sine is a continuous function, So what can you do with the limit? You can move it inside. And this is the same thing as sine of the limit as n goes to infinity of 1 over n. And what's the limit as n goes to infinity of 1 over n? 0. So you get sine of 0, which is 0. There's also a squeeze theorem, which I'll use in one of my examples below, but the squeeze theorem says if, say we have a sequence A sub n and C sub n. Notice here's A down here and here's C up here. A is the black dots and C is the blue dots. And let's say that B is somewhere in between them all the way through the sequence. Somewhere in between. It's bouncing back and forth, it's doing crazy things, but it's always between those two. And let's say both A sub n and C sub n go to L. Then what has to be true of the thing in the middle? It also has to go to L. So what that means is trying to find a boundary on either side of your sequence. There's one example down here, this one that I did right here, that works. No, it's this one, this example that I'm going to do down here. We applied that theorem. And last one that I want to mention, besides the squeeze theorem, is this absolute value theorem that says that if the limit as n goes to infinity of the absolute value of your sequence is 0, then the limit of the original sequence is 0. And I'll come back to that one in just a second. All right, so let's rush through these examples. It should be pretty easy for us to do pretty quickly now that we have those theorems. What's the limit as n goes to infinity of n over n plus 1? 1. Why?
Same for the same power.
So is it Bobo, Button, or HDC? HDC. Okay? Right, because you got a 1 up here and a 1 down here, so you divide their coefficients, you get 1 over 1, which is 1. That's what happens to this as you plug in larger and larger numbers. I mean, just think about what the sequence actually looks like. Consider, I know you see what the limit is, but again, I want to reinforce the concept of we're thinking about this as a sequence. So n over n plus 1, as n goes from 1 to infinity, is a list of numbers, and we're asking what happens to that list as you go further and further out. N over n plus 1, if you plug in 1, gives you 1/2, right? Plugging in 1 for n is 1 over 1 plus 1, or half. What's the next term? The next one? Because 3 over 3 plus 1. The next one's dot, 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 right? Eventually it becomes, I mean, you get really far out there, you're talking right? What is this doing the further out I go? Well, it's getting closer and closer to 1. It's getting infinitely close to 1. But you can see how to do it by using HDC. Exponents are the same. That's a C. Divide coefficients. Yes, I wrote E. Sorry. I kept saying DC. I blame the pen. You don't buy it, do you? Okay. Let's do the next one. Okay. So this is another one where Bobo Button HDC will work. Which one is it? I see a 1 here, but the problem is it's underneath the radical. Which means, what's the exponent on top? It's 1, but what's the 1 on bottom? It's actually half of that, because the square root of n is actually n to the 1/2. Okay? So it's Button, Bigger on top? No, does not exist. Okay? Or we'll say diverges.
So if you were doing this all for the online homework assignment, will we
I
write?
think it tells you to type in diverges.
Oh,
It'll tell you what to say if it does not exist. This should be log of n over n. Okay, so this one, Bobo Button HDC does not apply to because of the log. Okay, so what I'm going to do, well, first let's think this through. What happens if I plug in larger and larger in? Let's just think about it on top. What happens on top? Log of n, plugging in bigger and bigger numbers. It gets larger forever. This actually goes to infinity. What about the bottom? It also goes to infinity. So what do you think when you hear infinity over infinity? L'Hopital's rule. Okay, but L'Hopital's rule only applies to functions, not sequences. But we have a theorem. Theorem says if I can prove that it works for the function, then it will work for the sequence. So I'm going to look at limit as x goes to infinity of log of x over x. I'm going to use L'Hopital's rule. Remember, L'Hopital's rule works for infinity over infinity and 0 over 0. Do you remember what L'Hopital's rule says? Take the derivative of the top, derivative of the bottom, and then apply the same limit. Even works for limits at infinity. So what's the derivative of log of x? 1 over x. What's the derivative of 1? So this is the limit as x goes to infinity. Did the derivative of the top over the derivative of the bottom. So it's just 1 over x, which goes to 0. That's your answer. This is also 0. By theorem. Did I have a number? I don't think I numbered my theorems. By this one up here. Nope, I should number my theorems. By theorem above. By the theorem from above. Okay, so first of all, I just treat it as a function. That's why I put the x in there instead of the n. And I recognize that this thing was infinity over infinity. Okay? Whenever you have infinity over infinity or 0 over 0, then you can apply the trick known as L'Hopital's rule. L'Hopital's rule says the limit as x goes to infinity of f of x over g of x is the same thing. And I put the h over there. That's just an indication that I'm applying L'Hopital's rule. I don't know why it's an h. That's what my professor always did, so that's what I'm doing. But I do the limit as x goes to infinity of f prime of x over g prime of x. Derivative of the top, derivative of the bottom, and then try the limit again. As long as it's infinity over infinity or 0 over 0, then the limit after you've taken the derivative will be the same as the limit of the original problem.
So you plug in.
So I took log of x. What's the derivative of log of x? 1 over x. And what's the derivative of x? It's 1. So now I just simplify this. 1 over x divided by 1 is just 1 over x. So now, can I do this limit? Well, that's Bobo. It's bigger on bottom. Degree on top is 0. The degree on bottom is 1. So 0. Okay. Derivative. We've talked about this one several times already. We already know from up here, but it's divergent. Why? I mean, just think about the terms. It's a sound enough argument to just look at them and see that it bounces back and forth. -1, 1, -1, 1, -1, 1. So it's divergent. All right, let's look at this guy. Whenever you see a negative 1 to the nth in your problem and you're asking about convergence and divergence, it's a clue that you should look at the absolute value of that sequence and see what it does. Go back to this theorem that I told you right here. It said that if you have the limit of the absolute value goes to 0, then the limit of the original sequence goes to 0. So consider the limit as n goes to infinity of the absolute value of negative 1 to the n over n. If that's 0, then the answer to the original problem is 0. If it's not, then we don't really know anything new, and we'll have to try some other trick. But this is the trick we're going to use now, because it actually works. What is the absolute value of negative 1 to the nth over n? Yeah, the absolute value of the top is just 1. Right? I mean, the top for any n is either negative 1 or positive 1. Right? So no matter what n is, the top is either negative 1 or positive 1. The absolute value of negative 1 or positive 1 is both 1. And what's the absolute value of n on bottom? N is a positive integer. It's just n, and now we can apply Bobo. But the point here is, do you see how the absolute value just strips off the negative, even though it's negative 1 to the n, since negative 1 to the n is always 1 or negative 1, then the absolute value is going to be just 1. And now that goes to 0, okay? So by the previous theorem, we can say the limit as n goes to infinity of negative 1 to the n over n is also 0. So if the absolute value goes to 0, then the original sequence goes to 0. Now, if the absolute value goes to 4, then no, that doesn't help you. The theorem doesn't apply. It only applies when it goes to 0. Okay, last example, and then I'll probably skip the monotone convergence stuff because I don't think I need it for now. Stuff we cover more in the advanced class. If I have time, I'll come back to it. The last thing, I know I've got just no time left at all, but I'm going to apply the squeeze theorem. The clue that tells you the squeeze theorem is a good idea is the fact that the sines and cosines are in there. Because the sine and cosine both are functions that are always bounded between negative 1 and positive 1. Right? Recall that sine of n is less than 1 and bigger than or equal to negative 1, and so is cosine. So what that means, right, remember sine waves look like this? So it never goes higher than this and it never goes lower than this. And then this cosine wave starts here and does the same thing. Like that. So sine is never bigger than 1 and cosine is never bigger than 1. Sine is never smaller than negative 1 and neither is cosine. So if you have sine of n plus cosine of n divided by n to the 2/3, what's that going to be smaller than? What is the top bounded above by? What's the biggest it could ever be? Well, this sine is going to be bounded above by 1, right? And so is the cosine. So this is smaller than n to the 2, n over 2, 2 over n to the 2/3. Right? This sequence will never be bigger than this because the top can't get bigger than 2. Does that make sense? Because the output of a sine is never bigger than 1. The output of a cosine is never bigger than 1. So the biggest the top will ever be, could possibly be, is 2. But what does that go to? 0. That's another Bobo. Because the top is degree 0, the bottom is 2/3. But what about the bottom? What's the smallest it could ever be? -1, and another -1, right? Over still just into the 2/3. No matter what n is, the top is going to be bigger than a -2 over into the 2/3. And what does that go to? The degree on top, there's no n, so its degree is 0. And the bottom is bigger. Bigger on bottom is 0. So this is between two sequences that both go to 0. Which implies it goes to 0. Done. All right, I'm done. So this homework will be available here shortly for.
That means that this problem converges.
Yeah, converges. If it goes to a number, it's convergent. And it converges because of the squeeze theorem, meaning that this sequence is always between two sequences that go to the same thing. So the one in between has to go to that. All right, I'm gonna skip this whole monotone convergence stuff and move on to 11.2. Be sure you bring your notes back next time. I'll also have your test for you on Friday.